All right, good morning, everybody. Today I'm going to be talking about a recent work with my advisor where we use Coxeter groups to construct new families of quantum codes, and I've linked our archive preprint here. And so what's the premise of this talk is that quantum computers are inherently noisy. They're prone to errors, and one way we protect against this is to use something called the quantum code. In a quantum code, we take n physical qubits, and we have some way of embedding the space of k logical qubits into them. Right? And the way that we do this is through something known as the CSS construction. Right? And what the CSS construction entails, I need two collections of Pauli operators, X-type operators, which are tensor products of identity in X, and Z-type operators. And I need these two collections to commute. Right? But if I have this property, then the CSS construction tells me there's some way to construct a quantum error-corrected code. Right. And operationally for this talk, what this means is we're going to be trying to construct these collections. We're going to try to construct X-type and Z-type operators where the overlaps of their supports is always even. And the CSS construction tells us that we get out a quantum error correcting code from this. Right. And here's one way that we can get a CSS code. Take this polytope, this truncated octahedron. I'm going to put physical qubits on the vertices of this object. And I'm going to use the geometric structure to define X and Z type operators. One way I can do this, I can say there's a global X type operator, so X on every single qubit. And then for every face of the object, I'm going to define a Z face operator. So for instance, this hexagonal face gives us a weight 6Z operator. Right? And it's easy to see that every face has an even number of vertices. And so this means that Z and X type, in this case, must commute with each other. In particular, this quantum code ends up encoding 11 logical qubits into 24 physical qubits. There's another way to do this on the same object. I can actually let faces define both X and Z type operators. So I've just picked out two faces in each case here. This is sort of self-dual. Every face gives us both. If I overlay these pictures, you can see any two faces either intersect on an edge or intersect not at all. Right? And this implies that the intersection of any X and any Z operator must be either empty or an edge, which means that this overlap is even. And so again, I get out commuting sets of X and Z operators, and I get out a quantum code. In this case, I happen to get out a code which has 0 logical qubits. But we can play this game with plenty of other polytopes. I put some up here, for example, two n-gons, two n-gonal prisms, this truncated icosahedron, and then tori. I mentioned in higher dimensions. You may see in 3 dimensions, the torus is not a polytope, but in 4 dimensions, there is a way to embed it as a polytope. And we're going to use faces to define X and Z operators, just like we did for the truncated octahedron on the last page. But how am I going to actually construct these polytopes? And this is where Coxeter groups come in. You don't need to know much about Coxeter groups, but I'll include the definition here just for completion. A Coxeter group, which is also known as a reflection group, is given by generators. So M generators S1 through Sm, and they satisfy some properties. One, I want every generator to square to identity. So this is what I sort of mean by a reflection group. And the second thing that I want, in Euclidean space, we know that the product of two reflections is a rotation. And we want the same thing to be true in this sort of abstract setting. I want that if I take the product of any two different generators, there's some finite number Mij, which is the order of this operation. This is sort of equivalent to saying that this rotation defined by this product has a finite order. Right, and what are examples of Coxeter groups? The two most familiar are going to be the dihedral group. So I have two reflection operators separated by some angle, and their product is a rotation of order n. And then the symmetric group, which is generated by adjacent swaps. You can check that both of these satisfy the conditions that I put on the last page for a Coxeter group. And why do we want a Coxeter group? Well, if I take a finite Coxeter group with m generators, then I necessarily get out a polytope in m dimensions. So for these two examples, the dihedral groups give us the two n-gons. The symmetric group in 3 dimensions gives us the truncated octahedron, but more generally, it's a family of polytopes known as permutahedron. Right, what are the faces of these polytopes? This is where sort of the combinatorics of Coxeter groups comes in handy. Faces are something called standard cosets. So the vertices, which are again always the physical qubits, are given by the group elements. Edges are always given by sets W and W times Si, where Si is some generator. And if you know some group theory, you'll recognize that this is a coset of the subgroup generated by SI. This is true more generally. If I take any two different generators, look at the subgroup they generate, then faces are always cosets of these objects. And more generally, if I pick any I generators, subset J, and I look at cosets of the subgroups they generate, I always get out the I-dimensional faces of the Coxeter polytope. And now I'm ready to define a quantum Coxeter code. I'm going to take W to be a finite Coxeter group, and I'm going to have two numbers, two integers, Q less than R. They should both be less than M. The quantum Coxeter code of order Q and R has stabilizer sets given by the following. Every M minus Q dimensional face gives me an X operator, and any R plus 1 dimensional face gives me a Z operator. And why did I make these choices? Well, it's a pretty easy to show lemma that if I take any I-dimensional face and any J-dimensional face of one of these Coxeter polytopes, then whenever I plus J is bigger than M, I necessarily have even overlap. Right? And so that's why I chose these numbers. The sum of M minus Q and R plus 1 is always at least M plus 1, given that Q is less than R. And so the X and Z operators necessarily have even overlap, which means we get out a quantum code. In some examples of these, iceberg codes or quantum repetition codes are connected to the two n-gon. In a paper last year, collaborators and I showed that quantum Reed-Muller codes also fit in this picture. And the polytope they're related to is the n-dimensional Boolean hypocube. And we also get out some new families of quantum codes. I put up some properties here. I mentioned the torus gives us a new family of codes, which is not the same as the well-known Kitaev toric code. Right? And then the family of these m-dimensional permutahedrons gives us new codes as well. Right? What are some properties of these? So I didn't sort of say it, but the X and Z stabilizer spaces, so these spaces defined by face operators, are governed by something called classical Coxeter codes, which is actually what the preprint we posted on the archive talks about. It turns out that the logical operators, so I didn't mention this, but these are essentially undetectable errors for this quantum code. It turns out that the X and Z logic operators are also given by classical Coxeter codes. And sort of we have this nice picture where the stabilizers and logicals are always Coxeter codes. And that's a feature of all these quantum Coxeter codes. The dimension is easily computed from something called a W Eulerian number. Pretty straightforward to compute these things. There's some recurrence relation to count this. All right, and then maybe most interestingly, these quantum Coxeter codes have transversal operators in higher levels of the Clifford hierarchy. So there's this generalization of the Pauli Z operator, and applying this to faces of certain dimensions necessarily gives us logic. Right, some open problems from this work. The first would be, naturally, do other polytopes work? I only mentioned using these Coxeter polytopes. The answer is probably not. We really need this even overlap property, which is like a pretty strong regularity condition. At least in 3 and 4 dimensions, the only polytopes that have this property are actually given by Coxeter groups. What are the distances of the codes? So we have a conjecture for the classical distances, but we do know for certain that the quantum distances are at most 2 to the m over 2. We don't know exactly what they are, though. To study logic on quantum codes, one needs something called a symplectic basis. And while we know a basis for the logical space, we don't know if a symplectic base is. And then lastly, can the logic of non-Clifford operators be characterized? So these ZK face operators I mentioned. Can you give a characterization? And in our quantum Reed-Muller paper, we do exactly this for quantum Reed-Muller codes. All right, and with that, that's the end of my talk. Since I can't be there in person, please feel free to send me an email about anything, and then as well as here's the link to our preprint again. I hope everyone has a nice day.